something strange is happening beneath North America. Billions of years ago, the continent formed when several smaller chunks of rock called microcontinents collided and clumped together. Since then, it has remained relatively stable. But today, scientists have found evidence that the ancient part of North America, known as the Laurentian Craton, is losing its massive roots. These roots extend more than 200 kilometers down into the Earth's mantle, and are thousands of times larger than the tallest mountain on the continent. And if they're not anchoring the continent in place, what's happening to it? Stay tuned to find out. What keeps the continents from drifting away? Why does the ocean water stay salty? And how do we know the inner layers of the Earth exist at all? Our world is full of giant forces that are often invisible to us, yet they shape our lives every day. And now, back to the video. The Earth's outer layer, the crust, is broken into 8 major pieces, called continental and oceanic plates. And these plates move around on top of the mantle, the layer below the crust. Now, the plates are always moving, but the continents themselves don't seem to budge much, because they're mostly made up of ancient, igneous, and metamorphic rocks that are billions of years old. They're so old that their original composition has been completely altered by all the geological activity that has happened over the eons. And since these ancient rocks aren't being replaced, they're called part of the lithosphere, the rigid outermost layer of the planet, along with the uppermost part of the mantle. But, although the continents look solid as a rock, they're actually quite dynamic. That's because the continents rest on the asthenosphere, a hot, dense layer of rock within the upper mantle that behaves like a very thick liquid over millions of years. This means the continents can move and even drift apart, but that doesn't explain why they stay in one piece. Each continent has a central part that's particularly resistant to change. These pieces of ancient crust are called continental cratons. The oldest parts of the continents, the cratons, are almost entirely made up of igneous and metamorphic rocks, meaning they were formed through volcanic activity or by heat and pressure deep within the Earth. They're incredibly stable because their original mineral structure has never been replaced. For example, the oldest part of North America, the Laurentian Craton, formed about 4 billion years ago. It was initially made up of volcanic ash and sediment that cooled and hardened into granite. Then, over the next few billion years, the constant bombardment of asteroids pushed this landmass deeper and deeper into the mantle, until it became part of a supercontinent called Rodinia. As the plate tectonics shifted over the eons, the area became buried under hundreds of kilometers of new crust. Yet it still managed to remain largely unchanged. That is, until now. Geologists have found that the base of the Laurentian Craton is slowly melting and dripping into the mantle like caramel sauce down the side of an ice cream cone. It may sound unbelievable, but there's evidence that this strange phenomenon has been going on for at least the past 30 million years, and will likely continue for tens of millions more. This discovery was published in the journal Nature in August of 2023 by researchers from the University of Toronto, who used seismic tomography to peer deep beneath the Earth's surface. Seismic tomography is a technique used to create images of the inside of the Earth using seismic waves. Seismic waves are created by earthquakes and travel through the planet until they're picked up by a seismometer. By measuring the time it takes for a wave to travel from one point to another, scientists can determine the speed of the wave at different depths. In turn, this tells them about the composition of the material that the wave is passing through. Faster waves indicate a more rigid and less dense material, while slower waves show that the material is softer and more dense. This is why seismic tomography is sometimes called seismic travel time tomography. In this study, scientists measured how fast seismic waves moved through the mantle beneath eastern Canada. They focused on P waves, which are the fastest type of seismic wave. They also used a special technique to filter out waves that reflected off boundaries between different rock layers. This allowed them to measure how the waves were affected by the properties of the rock itself, rather than its surface. The resulting image revealed a surprisingly large cavity beneath the craton's root system. The team concluded that this cavity was created when the base of the continent began melting, allowing the root to sink into the mantle. If this sounds scary, it's probably best to remember that the Laurentian Craton isn't at risk of collapsing anytime soon. Even though the root is melting, the process is extremely slow. The region's crust is still anchored to the bottom of the lithospheric plate, which is currently moving towards the northeast at a speed of about 2 centimeters per year. This means that it will take tens of millions of years before the melting spreads far enough up the continent to affect the overall structure of the lithospheric plate. So humans won't be around to see it happen, but other life forms might. For most of Earth's history, the planet has been a dynamic place, with the crust and mantle churning around in a process known as convection. Hot material rises from the core and cools as it reaches the surface, at which point it sinks back down again to be heated up all over again. This cycle is driven by heat from the radioactive elements in the Earth's core, and it causes gigantic convection currents in the mantle. But over the past 600 million years, these currents have mostly stopped. Today, the mantle is cool enough to behave like a solid body, except in a few places where intense heat creates pockets of partially molten rock called mantle plumes. These stationary mantle plumes act as giant hotspots and have played a significant role in the formation of the continents. Their heat melts the cooler crust, creating magma that pushes its way to the surface, and once it reaches the crust, it piles up and forms mountain chains. But mantle plumes can pose a threat to cratons, because their immense heat can punch through the continent's protective root system and destabilize it. The craton's root system acts like an anchor, keeping the continent stable and preventing it from being broken up by plate tectonics. But without its root system, the craton could be ripped apart by mantle plumes or dragged down into the mantle by the asthenosphere. Scientists believe that the melting of the Laurentian craton's roots began when a mantle plume hit the base of the continent. The plume's heat caused the iron and magnesium in the rock to melt, leaving behind a gooey residue of aluminum, calcium, and sodium. But this isn't the first time this region experienced volcanic activity. Around 360 million years ago, the Mid-Atlantic magmatic province created a flood basalt province that covered much of what is now eastern Canada and the northeastern United States. Scientists believe that the plumbing system left over from this event is responsible for the current mantle plume, which is causing the roots to melt. This raises the question, why didn't the melting happen sooner? To answer it, the researchers turned to another technique called receiver function analysis. This technique involves placing a seismometer on the Earth's surface and recording the vibrations caused by an earthquake. By analyzing the frequency of these vibrations, scientists can identify the depth and composition of different rock layers beneath the crust. Using this technique, the team found that the Laurentide craton's roots weren't always as thick as they are today. Instead, they were once thin, allowing the heat from the mantle to easily penetrate them. Over time, the roots grew thicker, providing more protection from the mantle until the last volcanic eruption. When the eruption occurred, it melted away the majority of the root system, leaving behind only a thin, fragile layer of rock. If the melting continues at its current rate, the root will disappear completely in another 100 million years. But that's not necessarily a bad thing. Cratons that lose their roots become more active geologically, meaning they're more likely to produce valuable resources like oil and gas. Plus, it's just fascinating to think about how the continents are constantly changing, even if those changes happen over millions of years. Now watch how we know the Earth is hollow inside, or check out what happens to your body after you die.